Formula for centripetal acceleration. What's the formula for centripetal acceleration?
Go ahead. No, I'm still looking. I just
All right, I'm
found
going to
where
put
the
A sub
notes
C
are.
here as a placeholder. Substitution, I'll go ahead and do that's going to be Q, V, V. So what are we going to go ahead and remember it? Go for it.
Now I'm not so sure.
The worst that happens is you're wrong.
Well, acceleration, the centripetal acceleration would be instead of angular velocity, we had like a different symbol for it.
Oh, angular acceleration?
Yeah.
You're talking about?
Yeah.
Yeah, that angular acceleration is just not the simplest way to go on this one.
Okay.
All right, we got
Something moment of inertia.
Something moment of inertia.
well, there is the
So I see here a k sub r is equal to 1/2 I w squared. Omega. I figured it was something, but like I don't know what this is because I
that's
can't remember.
kinetic energy, rotational kinetic energy.
Okay. So I'm getting there.
What's the
Oh.
this one didn't have any other symbols.
Centripetal
Is what you're
acceleration.
saying, is what I'm wondering. Because I feel like
There are two forms of it.
Something about torque.
All right. You know, it's seriously moments like this. I'm going. If I had to memorize it at some point, would it have stuck a little bit better?
if you tell me what it is, I will then remember it.
I will then be able to repeat it for a
Yeah.
day and then forget.
It's just pulling it from the. Oh yeah. Okay. See.
Or omega squared r.
That's
So,
That's what
okay.
I was thinking was for.
All right, welcome back. So centripetal acceleration, the magnitude is v squared over r. So this is what we're left with. We have the magnetic force acting on this particle. It's equal to the mass times the acceleration. It is a centripetal motion problem. And let's just get rid of stuff. I know that a v is going to cancel out. There's a v there and two v's there. Now I'm trying to find radius of curvature, so let's solve for r. Let's see, I went r on top, so I'm left with mv. Let's see if I can write that better. mv over qv. And now it's a plug and chug. If we can remember what the mass of a proton is. Any of you happen to know it? I'm thinking of the mass of the electron. That doesn't really help.
Mass of a proton
There we go.
is 1.6726 times 10 to the negative 27 kilograms.
times the velocity, which I had at 3 million meters a second. Divided by the charge, 1.6 times 10 to the negative 19 coulombs, times the magnetic field, which I set at 0.075. And what do we get?
I got 0.41815. Meters.
Like you mean it.
Meters.
There we go. So if I had this situation set up here, the radius of the circle that it would go under is, somewhere about that. That's basically the radius. If I increase the magnetic field, what does that do to the radius?
Would it make it smaller or larger?
It is one of those
Smaller.
two. Why do you say that?
Because it's in the denominator.
Yeah. If I make b bigger, I'm increasing the denominator, which makes the fraction smaller. So in high energy experiments, you have very high voltages or very high magnetic fields, and you get these little curve in tiny circles. Matter of fact, the importance of this in physics, we start here. The velocity of an object, it's easy enough to figure out. You zip it up to near the speed of light, you shoot it at a target. All I need is a sensor here, I know the distance between them. If I shoot a particle through it, the first sensor says, oh, we're starting time. Second one, that's where we'll end time. I know the distance divided by time, I know how fast the particle's going, give or take.
Easy.
So I noticed, I guess this is my question. Directionality, is it mattering for velocity in this scenario? Because I know that we are using v without the arrow above it, even though I know it's a vector. So can it be negative in these scenarios?
Oh, well, I've indicated the direction it's moving that way.
Okay.
And so that's just the speed.
Okay. Yeah, okay. That's what I was curious about. Over there, would we have to encounter a problem where it would be negative?
Well, that's possible.
Okay.
Typically, as with the electric force problems, if you think through the direction, then you can be a little bit fast and loose with the signs, just knowing, oh, I know it's going to be going that way.
Okay.
So finding how fast it's going, easy enough. Finding the velocity of it, easy enough also, because if I have two sensors here and I get a hit here and a hit here, well, then I know it's traveling in that direction. Charge, well, we'll hold off on charge. Magnetic field, that's usually something that's controlled. You got a little dial there, and you can crank it up or crank it down. So, and radius of curvature, well, you can observe what the particle does in whatever you're using. If you have a cloud chamber, then you just look at the cloud, take a picture, and then measure. So if I start out with R is equal to mv over QV. Let's see, I want to get M and Q together, so M over Q is equal to RV over V. Or if you prefer, Q over M would be V over RV. R, you can measure. B, you control. V, you can measure. So now we're at the point where we can start to identify particles based on how it reacts. I shoot a particle into this field. I measure what the radius of curvature is. I measure how fast it's going. I know the magnetic field. I now have a ratio of mass to charge. That will narrow down greatly what the particle might be. Matter of fact, the other thing I could do is that if I have the magnetic field out this way and I shoot the particle into it, well, if it curves down like that, it's a positive charged particle. If it curls up like that, yes. Mathematically, V cross B is still the same, but Q is negative, which means the force is in the opposite direction, so it's going to be up. And perfect with it. And I think there's a master set question where I present the stuff to you, and then I give you, I think, 6 different particles it might be, and you have to determine which one it is. Now it gets really tricky when you're shooting a million particles at a target, and then you get a huge spray of stuff coming out of it, and then trying to figure out what's what. That's electromagnetism. So at this point, we've done force acting on a moving particle. We have not really done the magnetic field created by a particle. Do I want to subject you to that? Yes, I do. All right, so this is a single particle going through a magnetic field. Suppose I have a bunch of particles all traveling through a magnetic field. In other words, yeah, I could call it a current, but typically if I just have a single charge, we don't call it a current, even though technically it is. But let's say we have a current now flowing through. So I have particles constantly passing through this magnetic field. I have a wire here. My current flow is in this direction. I should be having a force acting on the wire. Which way will the wire be forced? So if I look at, I have some distance delta x here. Do a little fast and loose with some notation here. I believe you get the gist of it. So I have a force is equal to Q V cross B. Velocity. What is velocity? Math definition. Chapter 2.
Position.
There we go. that's Q, change in position over change in time across B. I'm just gonna move that delta T over here, so I end up with Q over delta T, delta X across B. Well, here's charge. This is the charge that's flowing. We take any particular point, charge flowing past a particular point with respect to time. What is that? I have current flowing across, let's just take some particular point on the wire. I have current flowing through that, across that point, Q, in a certain amount of time T. What is that called? Hint, chapter 20. That's the kind of thing that's going to be on the test.
Is it the current?
Yes, that's current. Delta X is really the length through which it is traveling. I don't care about the total length of the wire, I just care about the length of the wire that's in the magnetic field. So I'll call that just L. So I now have a formula for the force of a current going through a magnetic field. It's just a slight variation of the force on a charge. What the heck? Let's just do a quick and dirty plug and chug. Let's say I've got a current of 5 amperes flowing in the I-hat direction, or just say to the right. The length of wire is, we'll just say 3 meters. And the magnetic field strength is 2 Tesla. So one thing I really didn't mention there, I put a vector symbol over my L. So that length there is a vector, but what is the direction of that length vector? And why would you say that?
Because it's in relation to the starting point, like where it is, where the particle is starting to where the particle ends. So like
Okay.
its initial position versus its final position.
I'll buy that. I'll put it slightly differently. It's the direction of the current flow.
Okay.
So L is in the direction of the current flow. Now technically, but not technically, there's a certain point where you're going, well, shouldn't that be the current is a vector, but current's not a vector, it's a scalar. It does have a direction, but if I have current flowing into a junction and current flowing out of a junction, the direction of the current flow is really irrelevant. It does have no impact, as in whether it's going this way or that way into a junction. So just note that the direction of L equals direction of current flow. Now I know that moving charges creates a magnetic field. If we talked about the direction, it seems like we did talk about the direction of the magnetic field. Yeah, okay. So if I have a charge moving to the right, positive charge moving to the right, what is the direction of the magnetic field it creates? There we go.
Here we go. Towards us, out of port.
On top.
Yeah. And then on the bottom into port.
It gets weaker the farther out you go. And the same is true with a current. If I have a single charge, yeah, I've got that. But if I have a current, let's just assume that that's a wire and I have a current flowing to the right, same thing. Again, these assume positive charges. If I have a negative charge, I can either figure out what it is for a positive charge and flip it, or just assume that the negative charge is going opposite of the positive charge. So if I have a negative charge going to the left, I can treat that as a positive charge going to the right. So if I have two wires, current flowing in the same direction, I know that each wire will create a magnetic field, and each current will be influenced by the magnetic field created by the other wire. So let's go for some stunning visual effects. So I have current flowing to the right through the yellow and green wire. The yellow wire is going to create its magnetic field out on top and in beneath it. So I have the second wire, the green wire. It is going to create its magnetic field, and since it's to the right, out on top. And in beneath it. And I did that completely backwards. Just the green, the yellow is fine. Out on top.